So, hi everyone, I'm Dvir. Thanks for coming. I worked at Yahoo on video streaming until a couple of weeks ago, and soon I'm joining Roku, so be sure to check their booth if you haven't yet. And the topic of our talk today is converting between strings and numbers. So may seem a bit trivial to most people, but actually we're going to spend hopefully the next 90 minutes talking about it. So let's build a calculator. Nowadays, calculators can do many things. Some of them, I bet, can make your coffee. But for the purpose of the talk today, we'll just do a one operation calculator, one that can only do addition. Now, calculators usually, their user interface is this small screen and keyboard. And so the user types in the numbers and operation he wants to know the answer for. And so what the calculator will get usually is a string with all the user input. Then it will do its calculation and send a string back to the screen to display the output. So how do you write it in program? So there are many ways to achieve it, even if we confine ourselves to C++. And looking at all the different ways actually tells the story of the history of C++ and how it was evolved. So let's start at the beginning. All right, this is the function we will implement today. As I said, it takes two strings representing numbers, add them together, and gives us a string back to display. So the beginning for us today is in 1969, where Ken Thompson, an engineer at Bell Labs, started working on a new operating system. At the time, Bell Labs had a time-sharing system called Multics, and he thought he could write a similar system, which will be much simpler and smaller, and he named it Unix as a pun on Multics. Soon after he started working on it, he was joined by Dennis Ritchie, another engineer at the labs. And together they developed Unix and had the first release in August 1969. At 1971, they published the first programmer's manual. Here is Ken in later years. This photo is from a very cool website called Faces of Open Source. That quote is comprised of portraits of notable and unsung heroes who dedicated themselves to the creation and advancement of open source. So be sure to check it out. And so that manual already has 4 different functions for converting between strings and numbers. I don't expect you to be able to read all this, but let's focus on one of them. And this is called atoi, A for ASCII, if you've ever wondered. And it converts an ASCII character string to a number, to an integral number. Now, back then, Unix was written in assembly. C wasn't invented yet. And so you can see this is an assembly function, basically. And they wanted, Dennis came with the idea of rewriting Unix in a higher level language, which he basically invented for this purpose. And we know this language as C. In 1978, the first Dennis Ritchie and Brian Kernighan published the first book about C called the C programming language, now commonly known as K&R. By the way, this picture of Dennis Ritchie also from the Faces of Open Source website, unfortunately, was taken after he deceased, and so his brothers here are holding his photo. Here is the implementation of atoi from the first edition of K&R. You can see that the syntax of C has changed a bit since then. For example, the parameter types are written after the parentheses of the function here. But the implementation is pretty straightforward. We skip white space. We check the sign, if there is one. And then we go character by character, adding it to our accumulator and multiplying by 10 each step. And finally, multiply it by the sign and return the result. This is the implementation from the modern muscle library, another implementation of the C standard library. And you can see it hasn't changed much. Okay, this is, I think, from 2012 or something. So it's still working on your computers to this day. There's also the floating point version called A2F. This is, again, implementation from K&R, the second edition this time. You can see that the syntax of the function declaration is what we know now. And the implementation is very similar. We just do the fractional and whole parts separately. So currently in the C standard, there are those overloads of ASCII to number. Notice that A2F actually returns a double and not a float, even though it ends with F, so it can be confusing sometimes. And there's no float overload actually in the standard. Probably because they didn't know how to name it, given that A2F was already taken. Now for the opposite case, K&R also add I to A, integral to ASCII. The implementation is basically reversing the implementation we've seen before for I to I, and the string is generated in a reverse order actually, and then is reversed at the end. So now we can finally implement our addition using A to I and I to A and so on. So I did mention it before, but we would like our addition function to be able to work with integral or floating point numbers. So we implement two versions, one for integrals and one for floating points. And for the floating point version, we would also like to be able to set the required precision. So how many digits after the decimal point to present to the user. So the implementation is pretty easy, pretty readable, but we need to repeat it twice, as I said. So when converting from strings and numbers and back, there might be errors, unfortunately, and we need ways to deal with those errors. The typical errors we can come into are first, for the string to number direction, it might be that we didn't get any number in the input string, so no conversion was possible. It's also possible that we were given a number, but it is larger than the range we're converted to. So if we convert it to a char, for example, and we got 300, we can do the conversion. For the opposite direction, we write to some buffer. It is possible that we'll overflow if the number is too big again. Unfortunately, atoi doesn't offer any error handling whatsoever. So basically, if there was no conversion, you'll get 0, but assuming 0 is a legal output of your conversion, you can't know something went wrong. And for the out of range case, you'll simply get an undefined answer. So some number, but we don't know what. So to conclude, those family of functions, I called X to Y here, they have simple and intuitive API, but they have many downsides, especially they don't have any error handling. And yeah, I didn't mention it, but I2A actually was not standardized for some reason. And there are implementations supporting it. For example, the Microsoft implementation of the C library. But again, it's not standard. We're continuing with the history of C yet. This person, Michael Esk, or Mike, in 1978, he wrote a new I/O library for C called the Portable I/O library. And this library was integrated into release 7 of Unix. You can see, again, the cover of the programmer's manual for this edition. In fact, this person is responsible for the C standard I/O library as we know it now. And this manual included a new family of functions, Printf, Sprintf, and fprintf, that can take any format strings and any number of arguments and write them either to the screen, to a file, or to some character string. Printf actually was not invented by Mike Esk. It was inherited from previous languages. For example, Algol 68 already had a function called printf with a similar behavior, but Mike did add the other variants. So currently the standard has those overloads of Sprintf. There are also, and also the opposite direction called scanf, which gets a string and parses it and writes whatever it parsed to the output argument. There are also secure versions which are suffixed with _s, but to this day, none of the standard C libraries implemented them, including Microsoft has some implementation, but it's not standard conforming. And there's even a proposal to remove them from the standard. So basically, I would advise you to not use them. But do use SNPrintf, the second overload there, which at least gets the size of the output buffer and can avoid overflowing. And now back to our addition function. This is how we implemented it with scanf and sprintf. The implementation is pretty short, but it does require the programmer to know the different format flags. Most C and C++ programmers, I assume, are familiar with it already, but it's still some learning curve. And again, we need to repeat the implementation once for integral and once for floating points, because the format flags are different. This is so printf and scanf are highly customizable. I won't go over each possible customization here, but you can have different formatting flags for different numeric representations, like making it uppercase or changing the base and so on. So do check out the slides afterwards if you want more details. The error handling is a bit better than what we've seen before. So scanf will return us the number of characters it successfully converted. So if none were converted, then we will get 0. It will set errno, at least on Unix-based systems, if there was a number which is out of range for what we request. But printf or sprintf can still result in undefined behavior due to buffer overflows. So even though I sized my buffer to the size of the number, I forgot that sprintf also writes the null terminator, which will overflow. So to conclude, this family of functions is highly customizable. It does offer some error handling, but it's less readable. It's not, when you read the code, you can't see straight away that you do any numbers conversions or whatever. It's not specific for this purpose. And maybe less critical, you can only write to bases 8, 10, and 16. As Kevlin mentioned today, binary representation is highly used by low-level programmers, and we don't have it here. So in the 80s, Unix was split to 2 parts. There was a research team based in Berkeley that continued to develop what is called Research Unix, or BSD. And AT&T, the owner of Bell Labs, released other versions of Unix, more commercial, under the names of System 3 and System V. This is the manual for System V from 1983. And in this manual, for the first time, we have a new type of a new function to convert between strings and numbers called strtol. The standard has many overloads of this function for any numeric type from long and longer. So if you want a type which is smaller than long, you are expected to call the long version and then cast it to your required type. And it has a richer interface. So it takes a pointer to a char pointer, which it will fill with the position of where it stopped parsing the string. So then you can continue parsing from there if you need. And it can also take a base, this time any base from 2 to 36. At least for the integral part. So to implement our addition with strtol, unfortunately we don't have any function for the opposite direction. So I'm using I2A and F2A here. But for the string to number side, I'm using strtol and str2d. This time they named it right, so D is for double. But since we're in C, we don't have default arguments, so I need to explicitly pass null and 10 for decimal base. But other than that, it is pretty readable, in my opinion. strtol offers similar level of error handling as scanf. And so it will set errno in the case of out of range, and it will, for the non-conversion possible case, we can check this end pointer, and if it's the same as the start pointer, it means we didn't do anything. So to conclude, str2x is somewhat customizable. It has good error handling, but we don't have any similar way to convert from numbers to strings. And it's not generic. We have a different function for each numeric type. Finally, we come to the age of C++, created by Bjarne. And in 1985, as part of the Usenix conference, Bjarne published a new IO library called the Iostream library. So this library was designed to be type safe, to have a terse syntax and extensible, and basically to be the C++ alternative to Printf. So currently the standard has a rich hierarchy of classes as part of this library. Even though the first edition from 1995 only had Istream and Ostream for printing to the screen. The rest of the classes here were added in 1989 by a guy named Jerry Schwartz. So in our case, we want the output to go to a string, so we'll use Stringstream, which is a specialization of basic Stringstream. So as is the case for std string, it is a specialization of some basic class, and you can have other specializations for other character types. There's also an input-only and output-only variations of those classes, and it's recommended to use them if you only need one of the directions, because it's safer and the compiler will yell at you if you try to output through an input stream. So to implement or add the function, so as the promise of C++, we can finally write a generic function to do both integrals and floating points. But the syntax is not so readable, in my opinion. So we fed our input strings to an Iostream stream. So we're currently dealing with inputs. And use the input operator to extract the numbers. And then use Ostringstream to convert between the result of the addition back to string. We can set the precision and the fixed format in this case, and for integrals, it will simply ignore them. For error handling, we can call fail on the stream, and it will test if there was any error. And if we prefer, we can request it to throw exceptions in case of errors by calling the exceptions method. So to conclude, Stringstream is highly customizable. There are many formatting flags you can set. Similar to Printf, it only supports 3 bases, but it is generic and more secure. You can't have a buffer overflow if you get an std string which is dynamically allocated to match your output. So Stringstream was the answer, the C++ answer to Printf and scanf. This paper targeted for C++ 11 proposed the C++ counterparts to strtol, and also the opposite case for converting between numbers and strings called toString. So in the standard currently in C++ 11, we have those overloads of toString for converting from numbers to strings. Again, we only have int and up. And those overloads for the string to number direction. Unfortunately, they kept the naming of C, so we have a different named function for each integral type. And the API is actually a copy from the C versions, and the standard even mandates that those functions simply call the C function to do their job. So we're back to implement our addition function. We again need to split it to 2 because of the different naming. But if we just look at one of them, it is so far the shortest and I think most readable implementation we have. Unfortunately, it's not customizable, or toString doesn't have any customization. So we can't define the precision here. The error handling is done by exceptions only, which might be also a downside if you can't use exceptions in your code. But you can say it is safe. So to conclude, the C++ 11 functions have the simplest API. They do error detection, but they lack customizability, and they force you to use exceptions. So let's stop a bit for talking about the history, and let's talk about converting floating points to strings. So for any limited space floating point representation like IEEE 745, that if, for example, you use double, then you only have 64 bits to represent your number, then as you can assume, not all the real numbers can be represented using this format. So basically, if you look at the real number axis, you have little gaps between the numbers which are representable in this format. And actually, the gaps are getting bigger and bigger as the numbers grow. So here I have 3 numbers which are adjacent to one another. So no number between those 3 can be represented in a 64-bit floating point representation. And now if we want to convert the number in the middle here to a string, any string which will be between those midpoints, that means it is closer to the target number than to any of its neighbors, will give us the ability to uniquely identify this number in the middle here. So, for example, this string, which is 0.1 7 zeros and another one is such a string. So if we're given this string and we're told this is representing a 64-bit number, we can immediately tell that the number is this one in the middle here. But actually, there is even a shorter string that can give us this ability, and this is simply 0.1. So ideally, when we convert this number to a string, we would like to just get 0.1, and then we can know this was the origin number. Sometimes there are two shortest strings in this range, and in this case, well, the ideal conversion will return us the one that is actually closer to the target number. So the one ending in 6 in this case. So moving back to the history of C++, in 2013, or 15, sorry, Jens Maurer published a paper for the C++ standard that requested that the standard will have such ideal conversions, which it didn't have until then. And also, preferably, they will have a better performance than what was available before. He then continued to actually propose such functions targeting C++ 17. And indeed, those numbers got into those functions, got into C++ 17s under the names from char and from chars and to chars. So I don't expect you to read this font size. So I just shortened it, written it as a template, even though it is not defined as a template in the standard, just to have all the overloads in one declaration. So from chars converts between character strings to numbers. So we have two types of signatures, one for integral types, which takes a base between 2 and 36, and one for floating points, which takes a format. So you can have a fixed or exponential format and so on. The return value is a struct, which has two members, one for the pointer to where the parsing has stopped. So you can keep parsing from there if you want to. And one, the error code to signal any error that happened during the conversion. The opposite direction for converting between numbers and strings is called to chars. Again, I've written it as a template, even though it's not defined like that in the standard. And so here it takes non-const character pointers and writes the result to this range. For the floating point case, we have 3 signatures. One that also takes the format, and one that, in addition, takes the required precision. I'm not sure why they didn't use default parameters, but this is what we have. The resulting string is not null-terminated. It is important to notice. So you have to do the null termination yourself if you require to. The return type is quite similar to the other direction, only that the pointer here is, again, non-const. So those functions are part of the Charconv header, so include it if you need to use them. And to implement our addition, again, we can use a generic we can have one generic implementation. But to me, I think it is not so readable, especially if you're getting a string and you need to call its member functions to get the character pointers. And also, since, again, we're dealing with low-level character pointers, we need to do all the manual allocation ourselves. So here I used numeric limits to get the maximum number of characters a numeric type of type T can have. And that's the size of my initial buffer. And then after the conversion, I downsize it back to the actual size that was written by checking the return value. So as we mentioned, for error handling, we have the error code as part of the return value. So it will be set to proper values in case of non-conversion was possible, an out of range input, and a possible buffer overflow. So if you're given a buffer which is not big enough, again, we will have this error code. If you do want to throw an exception, you can do so yourself by constructing an STD system error with the error code you get. So this family of functions, it is somewhat customizable, and it is generic. Yeah, I didn't mention it, but I don't have to set any precision here because, as I mentioned, those functions are what is called the ideal conversion. So they will give you the shortest string that can identify the input number uniquely. So basically you don't have to use precision, even though, as we've seen, you do have overloads where you can define the required precision if you do want to. But those functions do require manual memory management, being low level. The code is quite verbose, to my taste, and yeah. So we're getting close to the current days. And so starting from C++11, where variadic functions or variadic templates were added, it was known that we can use variadic templates to have a type-safe version of Printf. And one of the people that was aware of this fact was Viktor Zverovich, who in 2012 started implementing a new formatting library called FMT. This library became highly popular, and Viktor proposed it for standardization targeting C++20. And indeed, it was accepted to the standard, and now C++20 has those new formatting functions. So this is the interface. It takes a format string and a variadic number of arguments. So there's an overload which writes the output to a new std string. And there's an overload that can write the output to some output iterator and also to a sized range. this is how the syntax looks like. The format string looks similar to, it was inspired by Python with those curly braces. But because it is type aware, unlike printf, you don't have to specify the type of your arguments. So you can have empty curly braces if there's no customizability needed. And of course, you can't get confused with the wrong type and then have undefined results. And in addition, it also supports user-defined types by specializing formatter class, which I won't go over today. For the opposite case, there's a similar library to SMT called scanlib, created by Elias Kusunen, which is the variadic answer to scanf. So again, the syntax is similar with those curly braces, and it gets output parameters and writes the parsed data to those arguments. This is also proposed for standardization by Elias and Victor together. Unfortunately, it didn't get in C++23, but I hope we will get it in 26 or soon, anyway. So to use scan and format for implementing addition, this is how we would write it. So again, I think it is pretty concise, but we can't have a generic function because std format won't accept a precision for integral types, which I assume is a good thing because it is safer. Personally, I don't like having output parameters, so using scan forces me to have to pre-declare the variables and send them as output parameters. Scanlib also has the scan value function that returns the output to you, and so you don't have to use output variables. This is, however, currently not proposed for the standard. The error handling is, again, using error codes. So this is how you would check for errors from the scanlib library. The result type it gives you is convertible to bool. So if it is false, it means there was some error, and then you can call a member function to get the actual error. This is true for both the no conversion possible and the out of range case. And for the buffer overflow, it is unfortunately not ideal, because if you call std format 2, where you give an output iterator and no size, you might get a buffer overflow, because basically it doesn't know where to stop. So what I suggest that you avoid using format 2 and only use format 2n, where you can specify the size, and then it will simply stop after it reaches this number of bytes. So scan and format are safe, type safe. They are generic. You can use them also for user-defined types. They're highly customizable. You have different format flags. Again, I didn't cover them today, but be sure to check the documentation. But again, the solution is somewhat verbose. It's not clear from reading it that you're actually doing string to numbers conversions here. So those are the functions we have in the C++ standard, or one of the future standards, hopefully. So now let's do some benchmarking and compare the efficiency of the functions we looked at today. So for this benchmark randomly generates ints and convert them to use those functions to convert them to strings. The benchmarks were run on my previous computer back at Yahoo, and so it's not really up to date to now, but I assume the numbers will be quite similar. And so you can see that Stringstream is actually much slower than the other options. And 2chars, as it promised, is indeed the most efficient one. But FMT or FTD format actually isn't far behind. So why are Stringstreams so slow, or Iostreams in general? So there are some people that keep saying that if implemented right, Iostreams can be as fast as any other solution, and simply no one had implemented them right for 40 years or whatever since they were invented. And some of the reasons are that the formatting flags are shared between calls to the stream. So when you call Iostreams, you pass the formatting flags one at a time, and each output operator needs to check all the formatting flags that the user might have called during anywhere in his code to know how to print the result. And it forces the use of locale. So you can't request it not to use locale, and this is expensive. For the opposite case, strings to integers, again, Stringstream is way behind, and again, from chars is the most efficient one. Scanlib can still have some optimizations made, I guess, because it's also not that great. For the double case here, I converted different precisions, but basically the results are the same. Stringstream way up, down is better here, I forgot to mention, and lower is better. And again, the C++ 17 Charconv functions are the most efficient. Similarly, the opposite case. All right, so let's conclude the standard, again, present or future standard functions we saw today. This is somewhat my personal opinion, of course, but I think we can say for sure that we did improve in time. However, in my opinion, we still lack a bit on the readability side. So both Charconv functions and scan and format are less readable than what we had previously with toString, for example. So my thought was maybe I can create a version of the Charconv functions that will be more readable. I started to implement it myself as a new library. And then I thought, wait a minute, there are many conversions libraries as we've seen, and there are many more than what we covered until now. So maybe I'll just add it to an existing library which already has a user base and so on. And so I looked at the next best thing to the standard, and this is Boost. So Boost also has quite not a small number of libraries for converting between integers and strings. The first one was written by Kevlin Henney back in 2001, and it's called Boost Lexical Cast. A disclaimer, I'm only mentioning the original creators of those libraries. There are other programmers who keep implementing and implementing new features and maintaining those libraries until today. So Boost Lexical Cast is basically a wrapper around Iostreams with a simpler API. So you have these single lexical cast functions, which you can use for both directions, for converting between strings to numbers and back. However, it does have some downsides. One of them is that it is a wrapper around Iostream, so it has the same not so great efficiency. But also it requires the types to be default constructible. So that might not be achievable but by the types you need. And it is not customizable. So there's only this interface and you can't pass any customization to the resulting strings. Another Boost library we can use is Boost format. So this is like the FMT-lib, a type-safe alternative to Printf. It has a bit different syntax, and it uses this percentage operator for passing the arguments. It was created by Samuel Kemp in 2002. And it, like Printf, it only supports the numbers to string direction. It doesn't have any counterpart for the other direction. Boost Spirit, created by Joel de Guzman, is a big library. I guess it can have its own 90-minute talk. This is a library for creating parsers, basically, and it can be used also for our task for converting between numbers and strings, but the syntax will be quite verbose. As you can see here, it's quite complicated. So I won't go over line by line here today, but this is a great library. I did used it to implement a compiler, actually, and be sure to check it out if you want to write parsers. And finally, in 2015, Vladimir Batov also searched for a conversion library. He looked at Boost lexical cast actually, and he wanted to improve it, basically to add types which are not default constructible and to have a better performance. But talking to Kevlin Haney, he decided instead of changing the lexical cast library to start a new one. And this new library is called Boost Convert. And so, in my opinion, this is one of the best ways to do numbers to string conversions. So first, this is what the library is written for. It's not taking some generic IO formatting library and forcing it for our case. So you can see we can call Boost Convert here. So first so the way Boost Convert works is by wrapping different backends. So as a backend, you can use any one of the standard libraries or standard functions we've seen. So in this case, for example, the backend is strtol. So you define this converter on line 8 and then use it for the actual conversions. So here is the conversion from strings to numbers and back. It uses a Boost parameter library for doing the customization. So here, this is how I pass the required precision. And as I said, here I'm using the strtol backend, and I can change it without changing any other line of code. So I can change it to use Printf underneath, or Iostreams if I want. If, for example, I already have types which are stream writable or readable, then I could use this together with Boost Convert to customize the output. And so, yeah, I'm not sure how readable it is, but so I found this library, and it didn't have support for the Charconv methods. And so I sent a pull request, and now at the next release of Boost 180, which is supposed to be released in August, will contain a new backend called Charconv after the Charconv header. And again, you can simply replace the converter by this type. The rest of the implementation is the same, but you'll gain a much better performance because you use the most performant backend, which is Charconv. Yeah, implementation is still the same. So let's go back here in a minute, for a minute. So Boost, as we mentioned a large number of times until now, conversions can fail, and they do quite often. And so Boost Convert simply delegates the decision of what to do with the failure to the caller by returning an optional. So it is a boost optional, actually. And so here, in this implementation, I simply called value on the returned optional. And if there was any error, optional will throw if I call value on an uninitialized optional. So this is the caller's choice, basically. If the caller prefers, they can call the value or method of optional to define a default value. So in this case, if the conversion failed, they will get a default value. Or better, they can delegate the decision of the error handling, or whoever writes this addition function can delegate the decision to its caller by returning an optional itself. So here I've changed the add function to return an optional, and I use the monadic interface of boost optional, or these flat map functions. If you're not familiar with them, so what flat map will do is basically look at the optional it is called upon. If it has no value, it simply returns an empty optional as well. And if it does have a value, it calls some method on this value. So in this way, you can basically chain your operations, and if any one of them fail, they'll simply stop and return an empty optional. So here I've defined the backend I want to use inside this function. If I know I'm always using the same backend, I can declare it outside of the function by defining this by default, by defining this by default struct, inheriting from the backend I want to use. And I also can customize the precision by defining the by default, or by defining the constructor to this class and passing the required precision, for example, or any other customization I want to do on my default converter. And then in the implementation, I can simply call boost convert and not pass it any converter, and it will use this default one. And so the implementation will be shorter in this case. And so hopefully, I recommend you to use boost convert starting from boost 180. And those were the many phases of number string conversions. Thank you.